All right, guys, welcome back. We're going to cover section C today as we keep talking about just how different changes in motion are recorded and measured, okay? So let's talk about acceleration. It's something that we use in our common language, but scientifically it might seem something a little bit different. The book uses the bold letter for vector qualities, okay, quantities. So acceleration occurs when there's any change in velocity. So since within velocity there's a direction, that automatically makes acceleration a vector quantity because it deals with velocity. Now there's three ways that velocity can change. The speed of the velocity can go up or it can go down. That's known as deceleration, by the way, when it decreases. Or because there's direction in velocity, the third way is for direction to change. Okay, so I've got a Ferris wheel here because even if those cars are traveling at a constant speed, their direction is constantly changing. They're constantly moving in a different direction. So their velocity is changing. So therefore they are accelerating. Okay, so speed up, slow down, or a change in direction. Another calculation, fun stuff. Let me move myself down just a little bit. There we go. We've got this formula right here, okay? So we've got acceleration equals a change in velocity over a change in time. And because we've got an additional time unit, so this would be our velocity unit, and there's our time unit, we're now going to talk about meters per second squared, okay? So anytime you're talking about acceleration, the label is meters per second squared. So imagine you have a race car and it's accelerating from 147 meters per second west to 119 meters per second west, and that took the time difference was 3.1 seconds. Okay, so just by reading it, we can see that it's slowed down, but that is a form of acceleration. So we find the difference between those, and it's similar to the displacement. We start with our final velocity and subtract our initial. Okay, so 119 minus 147 actually gives us a negative 28 meters per second. That negative is because it's slowing down. That implies deceleration. Okay, but that's just our velocity. That's our change in v. I have to change that or divide that by our time. So negative 28 divided by 3.1 gives me negative 9 meters per second, which I say is meters per second squared. Okay. There's another example right there. You can pause it if you want. Talks about cars. It shows you plugging the amounts in and you get an answer of 4 meters per second squared. Okay. That one actually has a difference in time, so you're actually subtracting the time as well, okay? Pause it, read it, know it, make it make sense. All right, so let's talk about falling objects now. Galileo spent a lot of time studying falling objects, and he actually discovered that all objects fall at the exact same rate as long as gravity is the only thing working on them, okay? So if there's no air resistance, all objects fall at the exact same rate, okay? So I've got different objects here. I've got, these are my density cubes, and they're all the same volume. They're all the same shape. And what that means is that air resistance is going to act on them the exact same way. If air resistance acts on them the exact same way, it's almost like air resistance isn't acting on them at all. So you would think that the much heavier one, the one with more mass, would fall faster, okay? This one's a lot lighter. You can hear it. Okay. If I drop these from the same height, and I can't really do it because you can't really see it, I'll show you in class, but if I drop them from the same height, they will actually fall at the exact same rate, okay? Because gravity is acting on both of them, air resistance kind of cancels out, they fall at the same rate, okay? But what if I have, something like a Kleenex and this heavy object? You would obviously assume that this is going to fall faster because this is going to float around in the air, okay? But if I remove the air, if I do this in a vacuum, if there is no air resistance, both of these objects will still fall at the exact same rate. And I'll prove it to you because I've got an amazing video to show you of that, okay? We call that falling without any other force but gravity acting on it, free fall. An object is considered to be in free fall when nothing is acting on it besides gravity. So I've been skydiving before. I got to do that right there. We always talk about that being a skydiver in free fall. That's not the same scientific free fall, okay? Because air resistance is still working on that person. When an object is falling due to gravity, gravity is causing it to accelerate, okay? And the acceleration rate due to gravity is 9.8 meters per second squared. And so what that means, the first second of fall, you get up to speed of 9.8 seconds. The second of fall, you've done that again. So after 2 seconds of falling, you're traveling 19.6 meters per second. And so every second you're falling, your acceleration is going up at a rate of 9.8 meters per second. Okay, that's kind of how that acceleration works. Until you hit this thing called terminal velocity. Okay, because we don't live in a vacuum, because there is air resistance, air resistance is kind of pushing up on an object. And so as the object's falling, it's going to eventually hit a maximum acceleration. It's going to stop accelerating because the air resistance has kind of balanced it out. Doesn't mean it's hovering in space or anything. It just means that it speeds up until it gets to a maximum rate, a maximum velocity, and then it keeps falling at that velocity, okay? All right, we also have to talk about circular motion. Circular motion is obviously anything that's moving in a circle, okay? So that Ferris wheel on that first picture would be an example of circular motion. And even at a constant speed, circular motion is accelerating, okay, because the change in direction. We get these terms with circular motion. One is centripetal force, which is an actual force, and then we get this thing called centrifugal force, which is kind of a perceived force. It's not an actual force, which gets kind of confusing, okay? So if I've got this object moving in a circle, I'm holding one of the strings. This string is what's keeping it in a circular pattern. Because this ball, as soon as I let go, it goes off in a straight line, okay? So let me kind of show this. If that's my ball right there, it wants to constantly go off in a straight line, but because I'm holding it, it's pulling it towards the center. That pull is the centripetal force. That is an actual force that's holding something in that circular pattern. Centripetal means center seeking, okay? So because it wants to go straight, but it's being pulled towards the center, it kind of splits the difference. And it's happening continually, okay? This is what keeps our planet in orbit around the sun, is a centripetal force. The sun is pulling us towards it. Now, if you're on the outside of that, so I don't know if you've ever been on one of those rides where it spins really fast and it pushes you against the wall. What you're feeling, what you're perceiving is the centrifugal force, okay? That's just the apparent force felt by this object. So this object is feeling a force in that direction. It's just an observed force. It's not an actual force. And it feels like it's being pulled away from center, but it's actually being pulled towards the center. Weird, right? That's what keeps water in a bucket, by the way. Fun fact, when you spin it. All right, another cool thing is projectile motion. If I throw a ball, it's a projectile, okay? But we all know that it's going to eventually hit the ground, right? So the path of a flying or falling object is determined by gravity, okay? The trajectory is that curved path, okay? So if I have a cannon up here, without gravity, it's going to keep going straight. Gravity's not going to act on it, it's just going to keep going straight forever. If I just drop the cannonball, gravity's going to pull it straight down. But if I shoot this cannonball out, it wants to go straight forever, but gravity's acting on it, and so we get this curved trajectory right here. That's known as projectile motion, is that curved trajectory. It's the curved path that the object follows because of gravity. Air resistance is also coming into play with this, okay? But here's something that's going to blow your mind. So let's say I have two cannons right next to each other, or actually I only need one cannon. I have two cannonballs. This cannon launches the cannonball at the exact same time that I drop this cannonball. They will both hit the ground at the exact same time. Okay, because they're both being pulled to the ground by gravity, and gravity's acting on both of them at the same acceleration. So they will both actually hit the ground at the same time. Wild. I'll also prove that to you with a video. And I have a way to demonstrate it in class. I can't do it on the video though. That's it. That's it for chapter 11. Good job, guys. See you later.